Alrighty, guys. For Algebra 2 today, we're doing starting a new chapter, if I could talk. We're going to do relations and functions. So lots of stuff going on today. We're going to graph relations by plotting points on the Cartesian plane, which we've done. Represent a relation using set notation, a graph, or a mapping diagram. State the domain and range of relations. Identify which relations are functions, and evaluate functions using function notation. So quite a little bit of a review, probably. All right, so let's review some stuff on the Cartesian plane to get us started. So first of all, it's the Cartesian plane, or the coordinate grid that we're talking about. It has 4 quadrants. So we have quadrant 1. It goes in that funny direction, right? Because it goes counterclockwise to 2, quadrant 3, and quadrant 4, which are labeled. I'm just labeling them a little bigger. Remember, our ordered pairs are always written as x comma y. We have the x-axis, the origin is at 0, 0, and our y-axis. Just to make sure we're on the same page with all of those. Okay, so it says graph and label each point. Remember, you always go right or left first, and then up and down for your graph, because it is x and then y. So 2, 4, we're going to go over 2, up 1, 2, 3, 4 to plot number 1, or A. And we can label it as A. All right, B is 3, negative 2, so we go over 3, 1, 2, 3, down negative, or down 2 for our negative 2. C is negative 1, 0, so we go negative 1, and we stay right there on our x-axis and put C. And D is negative 3, negative 4. So 1, 2, 3 back, and negative 4. So we're going to go 4 down, 2, 3, 4 down. And that's D. So starting off nice and simple, right? Easy review. I'm sure you're appreciating that. Whoops. Okay, so now let's get into another definition. Relation is any set of ordered pairs that can be represented in a set list, in a table, on a graph, or a mapping diagram. Okay, so that's what each of these is. So this first one here, ABC, this is your set list. So it's saying set A is equal to 1, 3, 3, negative 1, 3, 2, and 3, 4, those coordinates. Set B is a dog and a puppy, and a cat and a kitten. Okay, so all kinds of different ways you can write that, but that's a set list. Then we have our table, then the graph, and last but not least, your mapping diagram. All of these should be familiar to you from Algebra 1 and some from geometry. So it says represent relation E using set of ordered pairs and a table. And my set E is, I don't see it. Go figure. I don't have it on there. It should have been a mapping diagram of set E. So let me give you set E. Okay, so let me change my font here. So I've got negative 1, 1, and 3. And they go to negative 3, 1, and 5. Okay, so I gave them to you in a mapping diagram. And so this is set E. How funny. Okay, or relation E. So use it, represent relation E using A set of ordered pairs. Okay, so we have to use set notation. So we'll say E equals, just like this set notation up here. We've got to put the funny braces, and then we want to put them as a set of ordered pairs. So negative 1 pairs with negative 3. 1 pairs with, good, 1. And then 3 pairs with, excellent, 5. And then we close the with the brace for set notation. All right, in a table, okay, our x value is negative 1, and our y value is, good, negative 3. If our x is 1, what's our y value? Good, it's 1. When our x is 3, what's the y value? Awesome, 5. In a graph, we're just going to graph these 3 points like we wrote them here. So it's going to be -1, -3. So -1, -3. 1, 1, and 3, 5. 1, 2, 3. Excuse me, I was going to sneeze, and then I kind of lost it. Okay? Then it says state the relation's domain. Do you remember domain? Like domain and range are x and y values. Which one is which? Good. The domain is the x values. So that means the range is going to be the good y values. Perfect. Okay, so what are the, so to state the relation's domains, we're going to put D for domain equals, and we're going to list them just in a set, okay, like a set list. So our D is our x values, so we can look here, we can look here, okay. So it's -1, 1, and 3, and we close our brace. All right, so to state the relation's ranges, which we know are the y values, we're going to use the capital R equals the brace. And what are the range? What's the ranges? The relation's range. Good. -3, 1, and 5. Perfect. All right, that little note there says, okay, let's look at it for a minute. Relations can also be expressed in set builder notation. So that's a little bit different. Okay, so when we're looking at set builder notation, we're saying A equals xy such that y equals 2x minus 1. So we might write this in here, such that. Okay, so they gave us an equation, and then they're giving us a, we've got a colon there, or semicolon, pardon me, and we're saying x equals -1, 1, and 3. So you would take each of these and put them in to the equation, because this would then produce the set -1, -3, 1, 1, and 3, 5, the set that we have. Okay, so set builder notation, it's been a while since you've seen it, but you have seen it. So hopefully it comes back to you. Okay, example 3. State the domain and range of each relation. All right, so we're going to use that notation. I'm going to move this up a little bit more, actually. All right, there we go. Okay, so we're going to say D domain equals. Remember, domain is our x values. Range is the y values. So our domain is going to be just our x's. -2, 0, +2, and 4. Oh, I was going to put a parentheses instead of my brace. All right, and so my range is the other values. So it's going to be 4, 4, 4, 4. So my range is just 4. Okay, I only have to write it the one time. Okay, for B, let's change up our color a little bit. Our D, okay, again, it's our x values. All right, and we'll notice that we have, this is not a line, it's not continuous, or it is a line, it's not just a set of points, but it's also a segment. We have an open circle and a closed circle. So this is going to require that set builder notation. So we're going to say the domain is x such that x, so right here is at negative, right, we're thinking of our x value. So this location is -1. So -1 is open circle. Okay, so -1 is less than x. And then we have to go over to where this location is, right? And that is 3 over. So, and it's a closed circle, so x has to be less than or equal to +3. Okay, because we're only looking at the x values in between here. And we use less than because it's open, less than and equal to because it's closed. All right, let's look at the range value here. So our range, okay, those are our y values, and they're going from here to here. Okay, so we're going to go from here up to here, and they stop. So we're going to say the same thing. We're going to use set builder notation. It's y such that, what's the lowest number for our y value? Good, it's -3. Was that an open circle or a closed circle? Good, it was open, so that's going to be less than y. And then y has to be, so our y values are in this space. So now our y has to be less than or equal to, because this was that closed circle. And how high do we go up on the y's? Also, 3. Which, when I look closer, I apologize, the x value only went to 2, didn't it? It's hard to see when I'm recording sometimes, so I apologize for that. Let me get my pen back. So it should be less than or equal to 2. Make that change there. I apologize. You're probably screaming at me through the computer. All right, let's look at C then. And do the same thing for C. So we want our domain. So are we going to be able to write it as a set, just a list, or are we going to have to write it as set builder, our x values? So think of our x values, right? They're coming from here, and they're going all this way because our parabola is going that way, or our curve, I should call it. All right, so we're going to have to use set builder notation. So we're going to say x such that x is what? Well, it comes all the way down here to 0, right? So it can be, x can be greater than or equal to 0. Right, because this side doesn't end, so we just need the one expression, or the one inequality. All right, so let's look at the range. All right, the range is all these numbers, because see, this is continuing down and down and down, and it's continuing up and up and up and up and up. It'll go on up and down to infinity. So our range here is just going to be all real numbers. So it doesn't give us a list, a set list, and we can't use the set builder notation either because it's all real numbers. All right, let's clear it and flip over. Okay, next we have a function. A function is a relation in which every element of the domain is paired with one and only one element in the range. Okay, so the domain is paired with one and only one element in the range. Okay, so we can do the vertical line test. Is an easy way to determine whether a graph of a relation is a function. If a vertical line intersects the graph more than once, right? More than once, it is not a function. Then it is not a function. So if we have a mapping diagram, it's kind of the same way, right? Each domain is paired with one and only one element. So if there's no crossing, then we're in really great shape. But there can be some crossing. But it's important to know when. So this one is definitely a function, okay, because each domain goes to only one range. Okay. Here, 1 is fine. It goes to 3. But look at 3. It has 2 branches off of it. It goes to 1 and it goes to 2. 3 is the problem because this domain is paired with 2 ranges. So this one is not a function. And this set, F, looks complicated. But if we look, 2 is paired with one number. 0 is paired with one number. 2 is paired with one number. 4 is paired with only one number. So this one looks misleading, but this one is a function because each domain is paired with only one range. Okay, they all share the same range, but that is okay. All right, so example 4. Let's state whether each relation is a function. Okay, so think about each number. So we have to look at the domains. There's a 1, a 2, and a 3. There aren't any repeats. There's no repeats in the domain, so this is a function because each domain is paired with its own range or with a range. Okay, if we look at this one, what do any numbers stand out? You might think 5 stands out because two numbers go to 5, but 4 goes to 5 and 6 goes to 5. That's okay. The 8 is the problem, right? Because it goes to 7 and to 9. So this one is not a function. C, okay, we've got a graph here. Told us that if we have a graph, the vertical line test is the easy way to check it. So we just draw a vertical line, and here it crosses, and here it crosses. That means it's not a function. It fails the vertical line test. So not a function. D, we can draw a vertical line or as many as we need, but each time it's only crossing it one time. Like it only crosses the line at one point each time. So this is a function because it passes the vertical line test. All right, you guys are doing fantastic. Oh, there it goes. Okay. Then we're going to talk about function notation. When a function is expressed as an equation, so function notation is simply when a function is expressed as an equation. It's often written as f of x. Okay. You've seen this before, I'm sure. I know g of x, h of x, any of those things. That's function notation. Okay. So, however, what it says there is f is the name of the function. Okay. F is the name of the function. So sometimes you have f, g, h, k. The x tells you that x is the input. This is the number we're going to put into the equation over here. And then this whole thing tells you what the function does. We're going to take 2 times x. Okay, and it's also going to be your output, what we get out when we're done. Okay, so we can take an equation like y equals 2x minus 1, and we can change it into function notation. F of x equals 2x minus 1. The only thing that changed is the y. The y is now written f of x. That is it. And I know that seems ridiculous maybe at this point in time. It is going to be very beneficial in the future to use function notation because then you can put your x in there already. So it's kind of hard to explain how it's going to necessarily be beneficial, but it will. So the variable representing the values of the domain, x, is the independent variable. And you need to know that the variable representing the value of the range, okay, or the y, or the f of x, is the dependent variable. X is always your independent variable. Because it says evaluate f of x equals 3x minus 5 for d. Remember, d is what? Domain. Yes. For the domain when it is -2, 0, and 4. So what that means is our domain is our x or y values. Good. These are x values. So we're going to plug each of these in for x and solve the equation each time. And how we're going to do that is we're going to say, okay, f of -2. Okay, because I'm also plugging it in here so I know I'm putting -2 into the equation. So that's going to equal 3 times -2 minus 5. So this is going to be 3 times -2 is -6 minus 5. -6 minus 5 is -11. And so I know f of -2 equals 11, or -11, pardon me. So f of -2 equals -11. Okay, we're going to do the same thing. This time we're going to do f of 0 because that's my next number in the domain. That's going to equal 3 times x. X is 0 minus 5. 3 times 0 is 0. And then we have minus 5. 0 minus 5 is -5. So our f of 0 equals -5. All right, one more. This time we're doing our domain of 4. So we're going to solve f of 4 equals 3 times 4 minus 5. 3 times 4 is 12, minus 5 is 7, so our f of 4 equals 7. Okay, now the cool part about this is we know when we look at the answers, when we write it like this, or someone else writes it like this, x is -2 and y is -11. So you could write an ordered pair very quickly. Here, x is 0, y is 5. Here, x is 4, y is 7. You can very quickly write an ordered pair when you're using function notation. Okay, now a little bit trippy part, I feel like. So we have the function f equals, okay, we've got the set notation, -2, -11, coordinates 0, -5, and 0.47. Can also be expressed as x f of x such that, so just remember like earlier we had xy such that y equals, all we've done is replace the y with the f of x. So it's x f of x such that f of x equals 3x minus 5 when x is equal to -2, 0, and 4. It's the exact same thing as the problem here that we did. Okay, we're just putting it in set builder notation. So notice that set builder notation describes the function with a rule and the domain. If the domain is not given, okay, domain is not given, it is assumed to be the real numbers. So all of the real numbers. All right, so we have one more problem to get to there. Okay, this last one. Example 6. Graph the function x g of x such that g of x equals -1/2 x. And we have -2 is less than or equal to x, and x is less than or equal to 4. Yikes, there's a lot there. So there are some guides here. Okay, sometimes I'll take these out of the book to help you. So it says find several ordered pairs that satisfy the function rule, including the endpoints. That's going to be huge. So our endpoints are the numbers that we've got here. Okay, so we want to find ordered pairs that have to include those two. You need at least 3. I always say at least 3. 4 to 5 is fine, but at least 3. And then step 2, you're going to plot those. So let's go with 4. Let's pick -2, and we have to do 4. Those are our endpoints. And then we can pick 2 other numbers. So let's do 0 and 2. That way we split them all up. Okay, so we're going to plug each number into this equation. So our g of -2 is going to equal -1/2 times -2. All right, and I'm just going to keep my equation going. So it's -1/2 times -2. Negative times a negative is a positive 1. Excellent. So we have -2 and 1. Then I'm going to switch up and do g of 0. So I've got -1/2 x, so times 0. What's -1/2 times 0? Good, 0. So 0, 0. Next up, g of 2. So -1/2 times 2. Negative times a positive, negative, half times 2, 1. Good, so -2, -1. And the last one is going to be g of 4. Remember, -2 and 4 are our endpoints. So that's why I use those. So we're going to have -1/2 times 4. What's a negative times a positive? Good, so negative. Half times 4? Good, -2. All right, and it said graph the function. So now I'm ready to graph these. I have -2, 1, 0, 0, 2, -1, and 4, 1, 2, 3, 4, -2, 1, 2. Okay. So Since these have this limit on them, okay, we need to go back and look at that. This is less than or equal to, so this should be a solid. This one is less than or equal to, so it should definitely be solid, and includes all the numbers in between there. So we need to connect these. Okay, we need to connect them. Sometimes you don't connect them. It depends on how they're written, but because it's an inequality, it's saying it's the range of numbers in there, we do have to connect them. All right, that is it then for today. Have a great night. I'll see you tomorrow.